So this is lecture, and so what we're going to do today is we're going to talk about some of the axioms that we need or we want to use in investigating, our key players, investigating integers, investigating primes. As I was talking to a couple of people before class, it is very easy to subtly assume something is true without having the proof of it. A lot of times your intuition is reasonable, but there are times you'll make mistakes. And so what I want to do is talk a little bit about the building, the infrastructure we need to get into doing interesting number theory. So we've talked before about the natural numbers, the integers, the rationals, the reals, and the complex. Okay. For the most part, we're mostly going to be working with the natural numbers and the integers. Then we'll start going a little bit further into the rationals, which get interesting. Things become very different once you go into the reals and the complex. Here you start having continuity to work with. For the integers, we have a discrete set. For the natural numbers, we have a discrete set. The rationals, it's still a discrete set, but it's a very different type of discrete set. So one of the big properties we want to use is the well-ordering principle. So the well-ordering principle. Any set of natural numbers has a least element. And is it a unique least element, or could there be several least elements?
It's unique.
It's unique. I was a postdoc at The Ohio State University, not at A Ohio State University. Okay, you've got to be very careful. There could be multiple paths. What we are assuming for the real numbers, and I'm assuming a lot of these things, is you understand that numbers are comparable. If I give you two numbers, A and B, either A equals B, or A is larger than B, or B is larger than A. One of those relationships hold. And we have a transitive property. If A is less than B and B is less than C, then A is less than C. So I'm assuming a lot of stuff like this. If I have any sequence of natural numbers, there will be a smallest element. Okay. Would that be true if I looked at the integers? Would any set of integers have a least element? No. Take the whole set of integers. And once you know it fails here because the integers are a subset of the rationals, so it fails here, so it fails here. So this is something fundamentally special about the natural numbers. There's a stopping point. You can't go below 0. Okay? So then the question becomes, what are the consequences of the well-ordered principle? So the first thing is we're going to be doing the division algorithm. Given n and q greater than 0, there exists A and R such that n equals A q plus R. And 0 less than R less than equal to q minus 1. This turns out to be an exceptionally useful fact. And here, everything in sight is a positive integer. Well, except for R, which would be 0. All integers. So if you just think about it, I start off with q. If q is greater than n, then we just take R to be n. If q is less than n, I just want to keep walking up in steps of q. And then what would happen, sketch of proof. So if q is greater than n, take R equals n, and you're done. If q is less than n, I'll leave the case of q equals n as an exercise. Walk in steps of size q. So here's 0, here's q, here's 2q, here's 3q with the box maximum and stop. Here's n. Okay? And as I'm walking, I should have some number of q a little bit below. Say this is LQ. And then over here would be L plus 1q. be walking like this. And so how far could it be from LQ to N? Well, clearly it can't be more than Q, because that would push me all the way over there. And that, if I'm walking, I shouldn't have a gap larger than Q. I'm deliberately trying to do this informally and not do this rigorously. This is not a proof, right? This is a picture and some chalk writings. It seems reasonable. Yeah, I keep walking in steps of Q, and I see how many steps can I take until I go past. And I stop right before I go past, and that will give me the value I need for A, and then my remainder will be less than Q. But this has not been written up nicely. What do you think might be a good ingredient to use in doing this proof rigorously? What might you guess would be useful? Yeah?
Modular arithmetic.
So we could use modular arithmetic, but we haven't covered modular arithmetic. What?
Proof by induction.
Could you prove by induction? What else might be useful? I feel like Vanna White. We've just written down the well-ordering principle, right? Might be, I actually do sometimes prepare lectures. It's not always, spontaneous, spur of the moment, what do I want to talk about today. Maybe there is some reason the well-ordering principle is written on the board. Maybe it's useful for stuff like this, to make arguments like this rigorous. So how would we try to use something like the well-ordering principle? Well, we could look at n minus mq over all m such that n minus mq is greater than or equal to 0. Will that be a finite or infinite set of m? Finite. At most n possible m's, right? Because q is going to be at least 1, so I clearly can't take m larger than n. So there's a finite set. If I look at these set of values, there's got to be a smallest value, right? The well-ordering principle tells me this has the smallest value. So let A be where n minus mq is smallest. So now we have n minus aq greater than or equal to 0. If it equals 0, we're done. So, well, we can assume it's positive, because if it was actually 0, we'd be done. What can you tell me about the size of this? How large could it be? So what's a bound for how large n minus aq could be?
N.
So it clearly can't be larger than n, but I want something smaller than n. We're trying to say that we can write it as a times q plus r.
It can't be larger than q?
Yeah, it can't be larger than q. If this was larger than q, we could form something smaller. So at most, q minus 1, else a is wrongly chosen. So if we let r equal n minus aq, we see 0 less than or equal to r less than or equal to q minus 1. And that finishes the proof. The next thing we could do is we could try to prove that the decomposition is unique. So this proves the existence of a decomposition. How do we know that there's not multiple ways of doing this? So what would it mean to have two different ways of doing this? So note, if not unique, you could have n equals a1q plus r1 equals a2q plus r2. There's lots of different ways to show that this is not possible. Any thoughts? Yeah.
R would, if there were two solutions, then R would break the bound of 0 and Q minus 1. Not.
Well, we might have different values of A. So this has a pair A1R1, this has a pair A2R2. Maybe this one has a larger R, but this one has a larger A to compensate.
You could say, if it's not unique, one of the A's is bigger than the other.
Good. So break it into cases. General theme, do a lot of easy problems rather than one large problem. If you break it into cases, you have more at your disposal for each attack. So, case 1, A1 equals A2. Well, if A1 equals A2, what do you immediately get? Then R1 equals R2. So that immediately implies R1 equals R2, done. Do we have to handle A1 greater than A2 and A1 less than A2? No. My favorite logarithm is the W log. Maybe you've heard of the W log. Without loss of generality, right? So without loss of generality, we can assume A1 is greater than A2. Because the other case is symmetric. So in this case, we could write, if we have A1q plus R1 equals A2q plus R2, when we subtract, we get A1 minus A2q is R2 minus R1. What's the largest this could be?
Q.
I'm sorry?
Q.
Not Q. Q minus 1. Because R2 is at most Q minus 1. So the largest this could be is when R2 is Q minus 1 and R1 is 0. So this is at most Q minus 1. What's the smallest? This is at least Q. Because A1 is greater than A2, it's at least one more. And that contradicts the equality. Okay. So this is just how you would go through things very rigorously and show that the division algorithm works, it generates a unique pair. This stuff has to be done. Right now, you should be questioning why you're in this class if we're going to be spending all of our time doing stuff like this. The reason is sometimes statements that seem intuitively obvious are false. How many of you have seen Russell's paradox? I was going to say there should be at least 2 hands up right now because I know I did in probability. So the great Frege was coming up with an axiomatic version of set theory. And he had a beautiful version all ready to go. And I'm embellishing the story a little bit. And then little graduate student Russell says, well, what about the following? And Frege's critic goes, yeah, that completely invalidates everything. Yep, you're right. And so people were too cavalier in creating sets. People basically said, look, you can collect all objects that satisfy a certain property, and that's a set. And what Russell said is the following. Okay, well, let's let R, after Russell, be the set of all objects, X, such that X is not an element of itself. Most things are not elements of themselves. If you look at the set of all teams that have won a Super Bowl, that's not an element of itself. If you look at the set of all natural numbers, that's not a natural number itself. They live at different hierarchies, they live at different levels. So this is called Russell's set, or Russell's paradox. What's the most natural question you would want to ask about R?
Is R in R?
Is R in R? This is Bostonian, this is a fun lecture to give. Is R in R? Well, there are 2 possibilities. you know, case 1, R is an R. So, since R is the collection of all things that are not elements of itself, R in R implies R is not an R. Contradiction. So I don't even have to bother with case 2. It must be the case that R is not an R. Well, we're a little ahead of schedule. We might as well look at case 2. So case 2, let's assume R is not an R. Well, since R is not an R, by definition, R is the collection of all things that are not elements of themselves. What can we deduce? Also a contradiction. So in the wonderful situation where R is an element of R, if and only if it is not an element of R, this is not a well-founded set. So the idea that you can just take the entire universe of discourse and collect all things that have a common property is false. And you have to be very careful how you build up set theory. If people are really interested, it's worth seeing at least once in your life how you build up the numbers rigorously and carefully. I will just start with a small little spiel here because we're so close it's painful not to, and stop. There's only one set whose existence you can be assured of, although it does require an axiom. Anybody want to give me the set? The empty set, yes. So we'll call this Seinfeld mathematics. We're going to do a lot with nothing. All right? So we have the empty set. It has nothing in it. Can anybody give me a new set? The set containing the empty set. Wonderful. Can somebody give me another set?
The set containing the set.
So one thing is you could do the set containing the empty set, or you could actually do the empty set and the set containing the empty set. Use set also works, but this is a better. And then the next one is I can do the empty set, the set containing the empty set, and the set of the empty set and the set containing the empty set. Anybody want to guess what number this corresponds to?
We need one more bracket.
Do we need one more bracket? Probably, yes. Thank you. Anybody want to guess what number this corresponds to?
0.
0. Next number. Next number. Next number. Notice that 0, 1, and 2 are all subsets of 3. Here's 0, here's 1, and here's 2. So basically, less than is set inclusion. And this is a way to build up the integers. We will never do any calculations using this. But it's just nice to see how could you make the subject rigorous. What do you need? What can we start with? What kind of sets can we form? Sometimes we offer a course on set theory. It's a very good thing to look at. Okay, so we've talked in the past about what it means for a number to be prime. You've got to be at least 2, and your only factors are yourself and 1. Composite, you're at least 2, and you're not prime. And then 1 is a special number, it's a unit. There are a lot of results we would love to have, but actually require a little bit of work. So one of the first ones that we would love to have is the following from the book of the blatantly obvious. Hope. If P divides AB, then P divides A or P divides B if P is prime. That seems like a nice property to have. Would this be true if P was not prime? No, so we need P prime. 6 divides 3 times 4, but 6 does not divide 3, and 6 does not divide 4. So it's very important that we have primality. This is surprisingly difficult to prove, or it takes a little bit of time to prove. For now, I'm going to hold off on proving this, but just let you know that this is something that you have to think about. Generalizations of this lead to fascinating questions in algebraic number theory as to what do we mean by a prime. How many of you have taken abstract algebra? I have to keep my hand on. I've actually never taken abstract algebra. I've taught it twice, so don't worry, but never took it. Have you heard about irreducibles? Okay, so at least one person noted it. So there is a question as to how do you generalize the notion of prime in higher places. We like this property, that if a prime divides a product, it's going to divide at least one of them. One way you might attack this is through unique factorization. Every number can be written uniquely as a product of primes. Look at what's going on for A, look at what's going on for B. P should be on one of those lists. If it's not, there should be a problem. The question is, how do you make all of this rigorous? I had a friend who left math in disgust and became an engineer when he showed that something was an integer and it was between 0 and 1, and the professor then wrote, now you have to prove that 1/2 is not an integer. I said, I'm done. I don't want to spend my life doing this. The reason we do this is because occasionally these statements are wrong. And we really need to be careful, and going through these proofs really illuminate what's going on. So I will put this off to the side that at some point we will come back. This is a very reasonable thing. It's plausible. It's true. Professor Silva and I actually just wrote a short note on how to teach this. So I might actually have no choice but to use this in the classroom at some point. Either that or maybe again to come in as a guest lecturer so I can travel. All right. What I want to do now is I want to shift to the Euclidean algorithm. How many of you have seen or heard of the Euclidean algorithm? How many of you have seen the debate between Professors Gowdy and Adams on the Euclidean algorithm versus something else? I don't even remember what Professor Adams says is equivalent to the Euclidean algorithm because it's just such an undefensible position. I mean, he did the best he could, with a horrible, horrible side. The Euclidean algorithm is one of the most important algorithms in mathematics. I do not say this lightly. It is the basis of being able to do a lot of things quickly. It's one of the reasons why RSA, which we will do in this class, was able to work for so many years and was the gold standard for encryption. If you think of how much e-commerce goes on right now, the ability to verify who you are without meeting ahead of time, that's absolutely essential. If you could meet Amazon, if you could go to their company headquarters and you could establish secret passwords so that whenever you buy things on Amazon, they'll know it's you, you'll know it's them, that's great. Most of us are not going to be traveling to Seattle. And you might also want to go to some other sites other than Amazon. I think there are still a few other sites selling products online. You don't want to have to establish your identity with every single one by going down in person. You want a nice way to quickly verify. And so the Euclidean algorithm is used in a lot of encryption schemes to do things efficiently. And so the idea is the following. So Euclidean algorithm. Given x and y greater than 0, find the GCD of xy. So what is the GCD? This is the greatest common divisor. So it's the largest D dividing both x and y. How many of you have not seen the definition of GCD before? Related to the GCD is also the LCM, the least common multiple. Right? Everybody's comfortable with this definition of the GCD. Here's my question to you. If D is the GCD of x and y, and delta divides x, and delta divides y, what can you conclude?
Delta divides D.
Delta divides D. Is this immediate, or do I have to work for it? Seems immediate, right? What's the definition of the greatest common divisor? It's the largest number dividing both. That doesn't immediately imply that any other divisor also divides it. I don't know that the set of all divisors is somehow ordered and that the largest one has all the other ones going into it. It it seems quite logical, it seems quite plausible that something like this is true. I'm just trying to really demonstrate how easy it is to subtly assume things, especially things that are true. You know, this is true, but we need to prove it. True, but work. All right, so the question is, how do we find the greatest common divisor? So I need a volunteer to give me a really, really bad way to find the greatest common divisor. If it's a good way, you will be in trouble. I want a painfully slow. Thank you.
Test every number up to the lower of the two of them, and then take the highest one that divides both.
Great. So, bad method. Try 1, 2, 3. We'll assume x is less than 1. X. Take largest. That works. So the cost is order x. This is extremely bad. If we use this, modern commerce would crumble. Thank you. Is there any slight tweak we can do that would make this a little bit better, but still be a very bad algorithm? There's actually a small tweak you can do, yes.
You don't need to test anything greater than x over 2 and less than x.
Okay, so one thing is, so one improvement, go up to x over 2.
And you test x as well, because x might be over.
So it could be that x divides. Yes.
Did you do root x?
So this is not going into factorization. So if we were trying to do primality testing, we could definitely do up to root x. I'm not sure about this. There's a really small tweak to this algorithm.
Try them all for x, and then of the ones that x divides, see if those divide y, instead of doing all of them on both.
Okay, there's something a little bit better.
Start with x and go down.
Start with x and go down. Right? We're trying to find the greatest common divisor. Why are we starting at 1? Right? Theoretically, does it matter? From an implementation standpoint, yes, it matters. So start at x or x over 2. Unfortunately, the greatest common divisor is 1. You're going to have to go all the way down. So this could be an order x algorithm. It could be extremely slow and painful. But we at least have a way to find it. If our lives depended on finding the greatest common divisor, we have an algorithm. It may take too long. If people are interested later in the semester, we might talk about Ramsey theory. How many of you have heard of the friendship problem from Ramsey theory? So assume everybody whenever I give two people, they either like each other or they hate each other. So the question is, how many people do you need at a party before you are guaranteed there will be 3 people that mutually like each other or 3 people that mutually hate each other? Turns out the answer is 6. You can say, well, what if I needed 4 people to all like each other, or 4 people to all hate each other, or 5 people, or 6 people? And the great Paul Erdős to try to describe just how rapidly these numbers grow and how difficult it is to compute them, once said something to the following effect. If a fleet of alien warships were to appear over Earth and say that they will destroy us unless we can give them the value of 5, 5 in 1 year, we devote all of our resources to computing the problem. If they want 6, 6, we fight. And just these really simple problems, the computational cost becomes so high so quickly. The Euclidean algorithm is a much better way to find this divisors. All right. So let's try to think about what's going on. What does it mean to be a greatest common divisor? Let's consider, and again, I'll keep x to be less than y, numbers of the form ax plus by. I'm going to let a and b vary. Can you give me a number that will always divide this? Yes? 1. What else will always divide this? D. So this is always a multiple of D. we could look at all possible positive values of this. Right? So study all positive values. What do we know about that set?
It has a least.
It has a least element. There may be multiple choices of A and B that give you that least element. For instance, if I shift A to A plus y, and I shift B to B minus x, then I'm going to add an xy, I'm going to subtract an xy, there's going to be no change. So I can have multiple choices that will give me the same least element. Or if you want, I might as well assume that A is between maybe minus y and y, and B is between minus x and x. I can easily confine myself to that. So without loss of generality, negative b less than equal to, negative y less than equal to a less than equal to y, negative x less than equal to b, something like that. So well ordering implies there is a least element. What do you think that least element is? It seems like it should be D. We know it has to be a multiple of D. The only thing we have to determine now is what is that multiple. Because by definition, D divides X, D divides Y, it's going to divide the linear combination. So we know it's a multiple of D. We must show that M equals 1. Okay? Any thoughts on how we would do that? So we're close here. We've got it as a nice multiple of D. Yes?
Maybe we try to prove a contradiction that shows if the least element isn't D,
Okay.
that D isn't the greatest common GCD.
Okay, so let's go by contradiction. So let's assume that this is not equal to D. Then we've got to show somehow that this violates this minimality. Right. So assume it's not D. So what we want to do is we want to show that we could find something smaller. So how could we find something smaller? So let's assume maybe A star x plus B star y equals MD, and it's not minimal. For definiteness, let's put in a value of M. What would you like M to be? I'm sorry?
Wait.
We'd like it to be 1, but 7? Now this is still the minimal value. So if we choose anything else, say A tilde x plus B tilde y, what would that be? It would have to be something larger, right? So let's choose a number. Give me a number.
9.
9. So, again, what I want you to do is I want you to see how to prove things. I don't want to just write proofs on the board. I really want to emphasize how you attack. This is a pre-core class. Real analysis is not a prereq. Abstract algebra is not a prereq. I know many of you have taken those classes. That's great. I wish I had taken some of those classes myself. But I really want to spend the time now highlighting how we can get to these results. Well, we've got a 70 and we've got a 90. What should we be able to get?
2D.
A 2D. So if we subtract, we get a tilde minus a star x plus b tilde minus b star y equals 2D. And this violates minimality. Now, this is not a proof, but this is a really good approximation to a proof. It has the structure, it has the foundations. As a nice exercise, flesh it out. The real difficulty would be is if they were exact multiples of each other. If this was 7D and this was 14D. But as long as these numbers are a little bit different, we can do something like this. What algorithm are we essentially using right now? Well, we haven't done the Euclidean algorithm, so we can't use the Euclidean algorithm. The division algorithm. We're writing 9D as something times 7D plus a remainder. And because everything has to be multiple of D, the remainder has to essentially be 0. And this is giving us a problem now. We shouldn't be able to get a 2D. This violates the minimality. Right? So try to really write this up rigorously. Okay? Any questions on this approach? So we've now solved in principle not only that the GCD exists, the existence was not so bad, we got that by well ordering, we actually have a method to find the GCD. Well, the first method sucked. It tries all the numbers up to x. Now what do we do here? Well, we take A in a box, B in a box, and look for the smallest value. Oh dear Lord, this is even worse. We're going backwards. So using this approach gives us something on the order of x times y, or on the order of x squared. Just being brute force naive gave us order x. All right, so we really want to figure out a better way of doing this. But we at least have a method. The other thing is, this gives us not just the greatest common divisor, but it gives us the greatest common divisor as a multiple, as a linear combination of x and y. And if you've taken abstract algebra, this is extremely useful. So who has taken abstract algebra again? Okay, when you're looking at like Z mod, PZ star and stuff like that, and trying to prove inverse of elements, you've probably seen something like this being used. So this is an extremely useful fact. So it's not just that the GCD exists, but we have a good way of writing the GCD. All right, so what I want to do now is I want to end with the Euclidean algorithm. And at first, the Euclidean algorithm is going to look terrible. But then upon further review, it will turn out that it's actually extremely efficient. And my idea again is to give you the big picture, the broad brushstrokes, and then you can fill in the details, or I can give you some reading, it's in the book, and you can go through all the little nuts and bolts. So we have x is less than y. So we can write y as some multiple of x plus a remainder. And the remainder is going to be between 0 and x minus 1. Then we can write x as a multiple of R1 plus a remainder, where 0 is less than R2 is less than R1 minus 1. And then we can keep playing the game. Now we can write R1 as a multiple of R2 plus a remainder. Oh dear God, does this go on for an infinitude? Okay, why must it stop?
Well ordering.
I'm sorry? Well ordering, okay, not a bad statement. So why does well ordering imply that it stops?
Because our numbers keep getting smaller.
Our numbers keep getting smaller. The remainder is always at least one smaller than the previous. So it's going to take us at most x minus 1 steps. So what this is saying is that the Euclidean algorithm will run in at most x minus 1 steps, or x steps. Oh, right, that's as bad as the mindless brute force. But it will at least stop, and it will work. Okay. As a nice aside, I was a postdoc at Brown for 4 years, and there was a very generous donor to the library who loved Henry David Thoreau. And so Brown got a lot of Henry David Thoreau stuff, including his Harvard algebra book. And so I actually got to see Thoreau doing some mathematical scribbles and actually applying the Euclidean algorithm. And it's just nice to see the mathematics of this person. So we're going to keep going, keep going, keep going. And eventually we'll say we'll get, so this one is, the indexes is always horrible. It's 2 below this one. So we'll say Rn minus 2 is A n n minus 1 plus Rn, 0 less than equal to Rn less than equal to Rn minus 1. Minus 1. Okay. What can you eventually tell me about Rn if we go long enough? It's going to be 0. So we just run this until this is 0. Now here's where things are really nice. If D divides X and Y, what else must D divide? Divides R1. And if D divides X and R1, what does it divide? So the GCD of XY is the GCD of R1X. The GCD of these two is the same as the GCD of these two. The GCD of these two is the same as the GCD of these two. It just marches down. So eventually, here's your GCD. Okay? So when you run this algorithm, you get to the GCD. It's the number right before the 0. And now, I'm not going to go through it. As a nice exercise, unwind this. Because I can write y in terms of x and R1, and I can write x in terms of R1 and R2, you'll notice everything is going to be linear. I will get finally an expression of Rn minus 1 in terms of x and y if I run it upwards. A good way to do it is actually just choose a couple of numbers, 24601, 1701, and 2 numbers like that. Run the algorithm, see what you get. It's a really good way to understand what's going on. So here's the Euclidean algorithm. The runtime is at most order x. This sucks. So the question is it really this bad? Or perhaps this is just a really bad estimate. What we're essentially saying is, what would have to be true for it to take on the order of x steps?
D is 1. If there's
Not okay, so D is 1 is
five
one thing.
numbers.
That's one thing. But what else would have to happen on every single step? It's more than just D is 1. That's part of it.
Rn is equal to Rn minus 1 plus 1? No, no, that's not right.
Not quite right. So, in order to have as many steps as possible, what must be happening every single time?
The remainder is always 1 less than
The remainder is
last.
always 1 less. The remainders are as large as possible every single time. So what this is saying is life is bad and it stays bad. It never gets better. Every single time the worst possible thing happens. Do you think that this could always be the case? Hopefully not. So we've got about 5 minutes left. I'm sorry?
You should have Falcons, yes.
They had a good period of time, in the first quarter was even, second quarter they dominated, so they had a period of time when they were happy. So claim every 2 iterations decrease by a factor of 2. So what this is saying is r to the I plus 2 is less equal to r to the I over 2. So this is my claim. That every 2 steps, the remainder has to be at most half of what it was 2 steps ago. And if that's the case, then this is going to run really fast. This will imply that it runs in logarithmic time. Because instead of going up to x, I go 1, 2, 4, 8, 16, 32. So I basically have, consequence, the number of steps is going to be approximately the log base 2 of x, as 2 to the log base 2 of x is x. That's about how many steps it's going to take to move all the way up. Right, so we need to prove that every 2 steps it goes down by a factor of half. So the best way to do stuff like this is to break it into cases. Case 1, I've given this lecture a couple of times in my life. I know a really good choice for case 1. Assume Ri plus 1 is less than or equal to Ri over 2. To assume when I take my first step, I go down by at least a factor of 2. Well, then when I take another step, I'm still going to be fine. So that's a win. Right? So the other possibility, assume Ri plus 1 is greater than Ri over 2. So we haven't gone down that far. Okay, so now what we need to do is we need to just write things out very carefully. And this is where I absolutely hate the notation. All right, so this one is always 2 less than this. So try to get this right. So I want to have an Ri plus 1 over here. So then the 1 over here is going to be 1 less than that. So that will be Ri. This will be Ai plus 1. And this will be 2 less, so I minus 1. And then this will be Ri is Ai plus 2, Ri plus 1, plus I plus 2. And we have I plus 1 is less than or equal to I minus 1, and I plus 2 is less than or equal to I plus 1 minus 1. Okay. So now we know that Ri plus 1 is greater than Ri over 2. What can you tell me about A1? I'm trying to think if I've written things correctly, if I want. So we're now assuming Ri plus 1 is greater than Ri over 2. So here's Ri plus 1 in terms of, if we go up one level, we have Ri is less than or equal to I minus 1 minus 1. So Ri minus 1 is larger than Ri. Ri plus 1 is at least Ri over 2. This is going to be at least 1.
Okay.
Right?
You're subtracting at least 1 of Ri plus 1 from Ri, which means you're subtracting at least half of Ri, which means Ri plus 2 has to be less than half of Ri.
Right. So the question is just writing this down clearly in the minute or two that we have left. The idea is that because of how large this is, we want to get something small later on. Okay, so how did you want to phrase it?
So we know ai plus 2 is greater than or equal to 1.
Okay.
Which means ai plus 2 times ri plus 1 is greater than or equal to ri plus 1, which is greater than or equal to ri plus 2.
This is greater than or equal to Ri plus 1.
Yeah, which is greater than or equal to ri over 2. So now we're now subtracting something which
So when we bring this over,
yeah.
We get Ri plus 2 is Ri minus Ai plus 2 Ri plus 1. This is at least Ri plus over 2.
Right.
So it could be larger. So we know that this thing over here is going to be at most Ri over 2. And that's what we wanted to show. Well done. So we've shown that every 2 steps we decrease by at least a factor of 2. So I will leave you to think what would be the worst possible pair of x and y for the Euclidean algorithm. This tells us it's going to run at most log time. Maybe it does even better. Maybe if you had a better professor, he could have given you a runtime of log x. Or maybe there's some really bad inputs that take a long period of time to find. So I will let you look for those. Okay.